Greetings, my name is Eric Hale and I'm a substation engineer, and I'm preparing a series of training classes, and this is the first one of those. And the purpose of these classes are to give you an introduction to some of the key features that will form the basis of your knowledge that you're going to use in your job, and really will form the foundation for much of your career. I consider these very important classes. I hope you take them very seriously. And along the way, if you do have any questions, I'd like you to direct those to your department manager. And if you'd like, you can email me at eric.hale@powereng.com. A couple comments on this. These classes are classes that I've taught for the last 15 years or so. And it's a lot easier to put the class together in front of a live audience rather than recording them. So if there are a few rough edges in the presentation, well, I apologize for that. But the demand for training these days is pretty significant, and my time is limited. So this is really our next best option. And I do welcome any feedback that you have on the classes and on the content. A couple comments also. There are on future classes, a number of them require that you have certain drawings, and those should be available to you on PLC. If they're not, you need to talk to your department manager and get your hands on them before you watch the videos. The videos really won't go anywhere for you if you don't have those drawings. Anyway, with that, let's get started. Okay, this is again class 1, and it is a basic introduction to controls. And I like to start these classes off with a safety tip. And today's safety tip is to never go to a substation alone. Substations are not inherently safe places, and if you were to go alone and you were to get hurt or incapacitated, it's kind of hard to know how long you would be there until someone found you. Also, if it were something bad were to happen in the station, maybe not hurting you, but say a breaker inadvertently tripped, it's good to have another person to back you up on exactly what happened. So anyway, with that, let's move on. And here is what we're going to be talking about this class. First, we're going to give you a basic introduction to control logic, and particularly the type that is used in substations. I'm going to introduce 3 basic relay types, or simple relay types, that you'll see over and over in your designs. And then finally, I'm going to give you an application that demonstrates these designs. Okay, a key point in everything we cover today is that they're all really simple concepts. The complexity only comes when you start building them together and into larger schemes. But it's real important, so that you understand those, that you've picked up the basics and the basic building blocks that we'll be using as you go through this. Now, I want to start off with and talk about the DC station auxiliary power system. Okay, here's a drawing of the key components of a DC station aux system. We start off with a battery. Every substation should have a battery. Occasionally in large substations, you'll actually have 2 of them. Typically are lead acid, sometimes they're NiCad, and there are some other chemistries that are on the market and gaining popularity. We also always have a battery charger to go along with it. In fact, in some cases you'll actually see, for redundancy's sake, 2 battery chargers. And then those feed into a main breaker on a DC panel. And this panel is actually real similar to the one in your house. In fact, if you have a 12240 system that's a 2-pole system, they'll look really, really similar to this. Now, one difference is, this Symbology basically, this is a molded case circuit breaker, and then there's a little line between the 2 poles that indicates they're ganging together. And that means that if one pole trips, it will automatically trip the other pole, completely de-energizing the circuit. Okay. Coming off of this panel, what we'll do is we'll take a branch circuit that then runs out to either the yard equipment or goes to the relay panels, or a combination of the 2. And this becomes your control voltage. And this is how we're going to, what we're going to use to execute our logic and to operate equipment, primarily circuit breakers. And that will be actually the topic of our second class. Okay, the symbology that you'll see in this varies quite a lot. And I've thrown up here on the screen one sample drawing. This is from a really large substation. And you can see quite a few breakers and quite a few control voltages or control circuits. And each one has its little cryptic description of what it does and its functionality. And then there's some wire names and all to facilitate the wiring design. The formats of these drawings are often very different, utility to utility. What's really important, obviously, is that you understand your client's standard for these drawings and that you follow it, and that way everyone that's using them will be comfortable with them and be able to meet the basic needs of your design. Okay, the first relay that I'd like to introduce is a simple auxiliary relay. The symbology for this will use this symbol, which is basically a coil, and it can also be shown just as a circle, but more commonly as that little squiggly line. Now the output of these relays is typically an A contact, which would be normally open or open when it's de-energized. And you may also have B contacts that are closed when the coil is de-energized, but open when you energize that coil. Or you may have a combination of the two, and that we call a form C contact. Now, a key part of control engineering is that you always show the devices on your drawings in the de-energized state. Really fundamental and important, otherwise it will cause great confusion. Okay, an interesting facet of these, and I've got three examples that I'll show you here in a moment, is that each of them has a current rating for the contacts involved. And I'm holding up one that's a little flash cube relay. And then here is a smaller version of that. And I'll show a close-up of these here in a moment. And then same exact type, but a much larger version of it. And each one of these, the output contacts, have a current rating that you don't want to exceed, otherwise you'll damage them and end up having to replace them. And the basis of this current rating has to do with how current is interrupted when you're opening a contact. Now, in the case of AC, which is this sinusoid shown here, what happens, you'll go to open the contact, the contacts will pull apart, and inevitably they will not be at a current zero. And so as they pull apart, say they open up, start opening up somewhere around here, they're going to actually draw a small arc. And then as the voltage goes through zero, that arc will extinguish, and what will happen is then as the voltage then increases between the contacts, that arc simply does not reignite, and you have successfully interrupted the current. However, in the case of DC, which is represented by this line, there is no current zero. And that makes DC current far, far harder to interrupt. Now, since we use DC as our control voltage, this is something you need to have in the back of your mind as you design a circuit, a control circuit, is try to be aware of what is causing that current to interrupt as the current changes as your control scheme goes through its functionality. Real important concept. Now then, as I said, I've got three examples of auxiliary relays, and the first one is real small, and I refer to this as a little flash cube relay. You actually don't wire to this relay, you wire to a plug that has terminal blocks on it, and then you stick this into the plug. And if you happen to damage it, it makes it real easy to replace. But you can imagine that these things have very low duty contacts because they're very small. However, they're still the same basic components of this that we'll find in the larger one that I'm about to show you. Okay, here's kind of an intermediate one. It again has a different pattern for the plug as the previous one, but the same basic concepts. And if you look inside this, right inside here, you'll actually see a small solenoid. And that's how these things work. There's actually a solenoid in there that when you run current through, creates a magnetic field. Then that pushes a little plunger that then mechanically changes the position of the output contacts. Now you can actually see that a little more easily in this device, which is again the exact same thing. And what will happen, this is its de-energized state. When you energize the coil, it does this. And the contact outputs change from closed to open or open to closed. Okay, very simple concept, but it's one that we're going to see over and over again as we go forward. Okay, next I'd like to introduce some of the basic elements of substation logic. And there are three basic formats that we use for substation logic. Probably the most common is ladder logic, and that's really where we show our DC schematics. And it's really nice because it shows physically all of the different devices that we then connect with wires to execute our scheme. Now, with the advent of programmable devices, because when I started doing this 25 years ago, we really didn't have anything programmable. But now, it's completely changed, and with modern microprocessor relays, quite a few features of our relay schemes have to get programmed in. And to do that programming, we use Boolean equations and to actually plug into the relays, but for drawing and documentation, we use logic diagrams. So the first one here, this is a simple AND gate. I'm sure you've seen these before. And if A and B are both asserted or value 1, then C becomes 1. This is the symbol or the same exact logic, but in a Boolean equation. And then here is how we would depict it in ladder logic. And you can see this makes really good sense, because if that's closed and that's closed, then you will energize the coil of your relay. In this case, it's just a little auxiliary relay. And the output contacts from that auxiliary would then change state. Now then, the next type of logic is OR logic. And here, it's if A or B is asserted, or value 1, then C has a value of 1. Now, this is the way we would show that in Boolean equations. I've always thought it odd that you use the plus symbol for OR and the little multiplication symbol for AND, but again, this got started before I had time to input on it. And then this is how we would show this in a ladder logic format. Now, this particular version is real important because we use this for trip circuits. This way that either A or B can close or pick up, and then that would energize C, which could be, for instance, the trip coil of a circuit breaker. And that's how you would then trip the breaker and clear the fault. Okay, one other aspect or part of logic that we need to think about is not or opposite. And in this case, what we're saying is not A and not B equals C, or using normally closed contacts in ladder logic format. All right, this is kind of an example of what ladder logic will look like. And in this case, we've got a large microprocessor-based relay here that has a number of inputs and outputs. It actually breaks here and starts back up here. Has quite a few inputs and outputs on it. And the various control voltages are these lines up above, and notice they're labeled, and then a line down below for the negative. So you have positive on top and negative on the bottom. And again, the format of these things will change fairly substantially client to client. And it's really important that you follow your client's formats, because that way, I mean, they're the customer, they're the user, and they're going to want it done the way they're used to seeing it, so that it's easy for their people and their personnel to use. Okay, here's an example of what a logic diagram looks like. This is one that we will actually cover, this very one, in class 7. This actually is a breaker failure scheme. And you can see over here you have a series of inputs. Then you're going through AND and OR gates. There's a timer, and over here is actually a latch, and we'll cover all of these in subsequent classes. Then that logic then controls a variety of output contacts, and these output contacts are in that very relay that we just showed you. They're all of these right down here. And again, we'll cover this in more detail in subsequent classes. All right, this is your next topic I want to cover with you, and this is actually a homework assignment for you. You need to go and find a list of the ANSI numbering for various devices. And the one I've got here on the screen is actually one that I copied back in 1992, believe it or not. And it has actually changed a little bit since then. You'll notice that ANSI number 11 right here says reserved for future application. It is no longer reserved. Back then we didn't have microprocessor based relays, and now we do. And so ANSI number 11 is multi-purpose relay, and then there are a number of suffixes that go along with it that describe further what it does. Anyhow, I keep this one around for sentimental value, but what I'd like you to do is for the next 6 classes, I'd like you to have this with you as you're watching those classes. And what I think you'll find in here is about half of the devices that are listed on this are things that you will run into in a substation. For instance, 21, 67, 50, 51, 49, 63. These are all numbers that have meaning to us, and again, it's just an important thing. It's kind of the language that we use in this type of engineering, and you can think of it, if you want, as this is your secret decoder ring so that you can understand drawings and the terminology that is buried within them. Okay, the next device I want to tell you about, the next relay, is actually a control switch. And a lot of substations are actually going away from these. And the one that I have in my hand here is actually an old version. This is an GE SB1. And there are other product lines these days that we generally will use in place of it. However, this is an excellent visual aid because it's all open and you can actually see the contacts. A more common device is made by a company called Electro Switch, and all of its contacts are inside of a large cylinder and you can't see them, which makes it kind of not so great for as a teaching aid. Now then, let's take a closer look at this device. On the front, you can see the control handle, and then there's a little slip contact right here that tells you what is the last function that it did, if it closed or opened. And if you've last closed it, it will be red. If you last opened it, it will be green. And as you're doing this, you will see that there are contacts right in here that close and do that. Okay, these contacts occasionally are called upon to break DC current. And you will see, or if you were here you would see, that they are nice and fat and have a lot of material on them and are not going to be damaged by having to break DC current. Okay. The next relay I want to cover is a lockout relay, and it's ANSI number 86. And it is, okay, a lockout relay is basically, think of it as an auxiliary relay, except once you trip it and energize its coil, it will stay in the energized state until a human being turns the handle back and resets it. And this is an important concept because there are certain types of faults that when we clear them, We don't want whatever was, wherever the fault was, be it on a bus in a substation or in a transformer, we don't want that to be re-energized until a person has gone out and checked the thing and tried to figure out and analyze what went wrong, and most importantly, to make sure that it is safe for that piece of equipment to be re-energized. Now, there are a couple of types of contacts within a typical lockout relay. Specifically, they're the normally open contacts that you'll use to trip devices, perhaps to send transfer trips, and for a function that's known as breaker failure initiate. But there are also B contacts, which are normally closed, and those are used to supervise closing of circuit breakers. If a circuit breaker has been locked out, you don't want to inadvertently have it close back into what would be presumably a fault in a live condition. Okay, I'd like now to give you an example. I've already alluded to this of how we can implement some interesting logic for a circuit or for a substation. And I'm going to take our drawing that we had where we established a control voltage, and I'm going to draw in it a couple of contacts in parallel. And so that would be OR logic. I'll go with 3 of them. We'll label the first one 86, second one 21, the third one 5051. And this could be any kind of circuit breaker, and then we'll put here trip coil 1. So if we energize trip coil 1, what's going to happen is you're going to trip your breaker. Now presumably the breaker is already closed, and whatever we're energizing energizes and is in service. However, if you have an overcurrent, which is a 5051, or an impedance relay picked up, or a lockout relay picks up, notice it's all OR logic, then you're going to energize that trip coil and the circuit breaker is going to trip. It's very simple, nothing really fancy about this, and every circuit breaker has one of these. This is really fundamental, simple logic that you really want to have just an absolute intuitive level understanding of. Okay, if we go over to, this is a particular trip scheme, and right over here in the drawing is the circuit breaker, and we're going to cover this in great detail in the next class. And right up here are all of the different things that will trip that circuit breaker. And in this case, they're not drawn out, they're just listed and with drawing references to the drawing that they actually show up on. But in a wiring system, those are all wired in parallel, so any one contact can close and trip that circuit breaker. And that's how trip schemes work. So in conclusion of this class, we've introduced a number of concepts that we're going to build upon as we go through a further investigation and introduction into substation control logic. Important to note that no single concept we cover is complicated, but you do get complications when you combine them up, increase the numbers of building blocks that we throw into the mix, which is why it is incredibly important that we all understand the very basics before we dive into this. That concludes the first class. I look forward to seeing you all in the next class. Thank you.